Okay, so what we did last time was we proved that if an analytic function has, if there's a point, if an analytic function in a region, if there's a point where the function is 0 and all the derivatives are 0, then actually the function needs to be 0 everywhere, right? So basically, we show the following theorem, and now we're going to use it now to actually classify quite a complete way what kind of singularities analytic functions can have. Okay, so let f in a region be analytic. Okay, if there exists a point A in this region such that f of A is equal to 0 and all derivatives of A are 0, then f equals 0 in all of. Okay. So f is identically 0, right? That's oftentimes what we say. Maybe I'll use another color. Okay, so this is already something very different from how functions over reals behave, right? It's already something quite special. But now it gives us, right? This has many applications, and one of which I think is maybe the most surprising, perhaps, right? And we saw a little bit of it last, like on Tuesday, rather quickly, was that, let's say that f, okay, so take f again, let's put the same player, so take f omega to c, analytic, and not identically 0. Okay, functions that are identically 0 are not so interesting, so let's take one that's not identically 0. Okay, so now let A be a 0 of f. Okay, so f of A is 0. Right, but by that theorem, we have that there must exist, right, some k positive, right, such that, well, let me use n. Let's use n. That's the same letter we use over there. There must exist some n such that fn, right, of A is not 0. Okay, and let's say that, right, because otherwise if all of them were 0, then the function would have to be identically 0. And let's take the smallest one. Okay, so take smallest one. Now, so there must be one for this is not true, and we say, right, so we say that A is a 0 of order n. I mean, usually this is called h, so let me switch the notation to h. Okay, but let's see what happens if we do that, right? Right, if we do that Taylor, right, the Taylor, like, I guess it's not quite a series, but the Taylor theorem that we saw, right? So let me write it exactly in the way that we saw it. Right, we saw that f of z, right, was equal to f of A. Okay, there are several Taylor theorems. This is one of them. right? But it's the one we saw. In particular, there's the Taylor theorem where you can actually take a series. We're not taking series yet, right? So we saw writing this exactly how I wrote right before. So we get 1 factorial f prime of a plus c minus a squared 2 factorial f second derivative of a plus all the way 2. And then we have, right, f of like some fh of z, z minus a to the h, okay? Right, so we saw that we can always expand the function this way, right? You're used to Taylor's theorem where you take an infinite expansion, and we will do that, but for now, just finite. And what we know is that, right, this is analytic. Okay, and so, right, and so if I take the smallest h such that this is non-zero, right, then all of this are 0, and I just get, right, f of z needs to be equal to f of h, fh of z, z minus a to the h. Right? And so because now if I take the nth, it must be, right? It must be A is non-zero. Right? Because let's do this maybe slowly. Let's take h derivatives of f of z. Right? So if we do that, we get, right? There's the terms where this gets differentiated less times. This is, of course, 0. And then there's one term where this, right? There's one term where this gets differentiated exactly each times, and this doesn't get differentiated at all. This is the only term that can be non-zero, so it must be that this is non-zero. Okay? So what this means is that I can write, effectively this means that I can write, so we can write f of z equals z minus a h times fh of z such that, and that's important, fh of a is non-zero. Right? So basically, the 0 at a is of order h, just like if it was a polynomial, right? If these things were polynomial, this was a polynomial that wasn't 0 on a. This is exactly the order of the 0, a, for the polynomial, right? So it's behaving a lot like polynomials. But this now gives us something, I think, even more impressive. Okay, so let's take another step. So because we can write it this way, right? And we know that did I write h everywhere? Yeah. That fh of a is not 0, then there must exist a neighborhood, right? There must exist some delta positive such that, right, f h of z is not 0 for all z near a. Right? Why? Because fh of z is analytic, in particular it's continuous, right? And so if fh at the point a is non-zero, there must be a little neighborhood around it that's still non-zero, right? And so there must be some neighborhood for which it's non-zero, okay? But so if that's the case, let's take z in this neighborhood, right? Let's take z such that a minus z smaller than delta and different, right? And z different than delta, than a, right? This is what's called being in the punctured disk. It's oftentimes the name that is given for this, right? So z is inside the set of z such that 0, right? This is often called the punctured disk or punctured neighborhood. Punctured disk or neighborhood. Okay, but if we do that, then let's see what happens to f there, right? So f of z is equal to z minus a to the h times fh of z. Okay, but if this is the case, right, then for z here, this is non-zero, right? Because z is not equal to a, so z minus a is for sure non-zero. But by hypothesis, this is also non-zero. Maybe I shouldn't put 2, otherwise it might look like I'm saying equal. Right, this is also non-zero. And so what this means that f of z, right, f of z is non-zero in this set, in a punctured neighborhood. Okay. Sometimes we don't include the word punctured just because, you know, sometimes when you refer to neighborhood, you refer it without the point also, but let me use the word punctured. So what does this mean? This means that if the function is not identically 0 and I have 1, 0, then I cannot have any other 0 in the neighborhood, or there must exist a neighborhood such that there's no other 0 there. So in particular, what this means is that zeros must be isolated. Right, so we get a theorem, like we just proved the theorem, right, that if f from a region to C is analytic and not identically 0, then the zeros of f are isolated. The zeros of f are isolated. Okay. Right? This doesn't need to be true for necessarily for smooth functions over the reals, right? But here we're already seeing very nice properties. This, you know, might not seem that surprising, but let me reformulate it in some other way, right? Let me say that let S, right, inside the complex numbers be a set with an accumulation point. Right, just a set where the points are not isolated. Accumulation point. Right, many things have accumulation point. I mean, right, example, say a curve, an open set, right, just some sequence with a limit. Many, many examples. Okay, but let S be a set with an accumulation point. Then, if f of z is 0 for all z in S, then f must be equal to 0 in all of the region. Okay? And this is again quite. Right now, I mean, it's just the same theorem exactly. I'm just reformulating it. But if you want to know if a function is 0 everywhere, you just need to check it in a set with an accumulation point. And, you know, this can sound even cooler if I now formulate it in slightly a different way. I'm just going to use, if I have now f and g, right, and this is usually called, I think, the identity principle. I'm just going to use the same thing, right? If I have f and g analytic, then f minus g is analytic, and so this theorem holds. But the 0 of f minus g is just a point where f matches g. So I can now formulate the theorem in another way, which is if f and g are analytic and coincide in a set with an accumulation point, right, then f equals g in all the region. Okay, they must be the same function, right? And this is, I think this is a pretty cool theorem, right? This is definitely not true, over, right? It's definitely not true over the reals, right? You take all of the complex plane. Imagine here the complex plane. Now you take some set with accumulation point. It can even be just this curve, right? Take some curve. If you have two functions, both analytic and C, that match in this curve, they need to be the same everywhere else, right? And so this is already giving you, some maybe intuition is not the right word, but some insight in how, maybe you've heard words like analytic continuation of functions and things like this, right? And here you're seeing potentially how powerful such an idea can be, because if I know the function, say, in just a line like this, there's only one. If there is a function that's analytic in C, there can only be one, right? And so that's why so many times we can define such a thing as an analytic continuation, a function that is equal to something that we want it to be equal to in a certain set and is analytic in a bigger set, right? And this is what allows us, in part, to argue that, at least it's unique. We maybe will say in a couple of weeks more about when is it that such a continuation even exists, but at least now we know that it's unique, right? And in particular, if I have just a small set like an open set, if I know what the function is valued there, then I know what the function is valued everywhere, right? And this is definitely not true over the reals, right? Over the reals, I can have, there's compactly supported very smooth functions, right? There cannot be such a thing over the complex numbers, right? If a function was compactly supported, right, only took non-zero values in a compact space, then the zeros would definitely have an accumulation point, right? Most, and so the function would have to be 0. So in particular, there's no such thing as compactly supported complex analytic functions, for example. Okay, now we're going to talk about singularities and attempt to classify the different singularities. But before I actually show you the theory, which has, a fair amount of calculations, but it's not the calculations that's important, it's the conceptual idea. Let me just tell you first how this is going to play out, right? Basically, what's going to happen is if we have a function f, right, there's some singularity at A. Let's say this is A, some singularity. Right, and we have some set around it where the function is analytic, except for this singularity. What's going to happen is you might imagine that if f, right, we have we had already this theorem that, as long as f doesn't grow too fast around A, then it was a removable singularity, and we could just take it to be some functional value there, right, given by the Cauchy integral formula. But there's another option you might have, which is that f, right, as z, the limit, say, as z goes to A of f of z goes to infinity. Right? Let's say that you have something like this, like think of f of z maybe, right? Maybe f of z is like 1 over z minus a, or 1 over z minus a square, or something of this type, right? Then this is definitely not a removable singularity, right? I can't just go and put a value there. It would be plus infinity. However, if you have such a thing, you can just take, right? very close to a, this is not 0. So you can just take the function 1 over fz, g of z. And this function has a removable singularity. And so you can use all this theory that we were developing to understand very well what 1 over fz is doing. And this will let us understand what fz is doing. So this is what I'm about to start now. But the key idea is that if the function goes to infinity at a point, you just treat 1 over the function, right? Because that goes to 0. And we have ways of, if we can control the functions, of removing singularities using Cauchy integral formula, right? This is going to be this is the vision of the next 20 minutes or so. Okay, so let's take our object. So f analytic, right? We're just going to study the function around the point A, so it doesn't matter which region it is. It's just going to be analytic in a disk around A. So it's analytic in Z, in the set Z, like Z such that Z minus A. Okay, let me just write like this: Z minus A smaller than delta and bigger than 0. Let me just... Okay, so it's analytic in the punctured disk around A. Okay, and now we can say, okay, let's say if, and now we want to study, right? So maybe before I write this, the goal, right, will be to study the singularity. Right, will be to study the singularity at A, right? We want to know what's happening at A. Okay. So first, if the limit as z goes to A of z minus A f of z goes to 0, right? These were these exceptional points from Cauchy's theorem. Then there's no problem at all, right? Then singularity at A is removable. Okay, so we know this gives us no problem whatsoever. Okay, so let's think now of a different scenario, and this scenario is that, let's say, just as I said before, that the limit as z goes to A of f of z goes to infinity. Right? So you'd expect, I mean, if things are nicely behaved, right, if this doesn't go to 0, then basically this is this times, right, divided by z minus A, which goes to infinity, so maybe this should go to infinity, right? Okay, in particular, I mean, we should characterize this way and not with z minus A times f of z, because, otherwise there would be potentially, like, take the function 1 over z minus A. If you were to multiply z minus A here, you would get 1, right? But if you think in nice functions, you would expect to get either this or this, at least intuitively, right? If you think of polynomials, that would definitely be the case. Okay, but if this is the case, then, See if I have another chalk. Then there must exist delta prime such that, right, smaller than delta, just because I want to be inside the place I am, such that in, like, I want a point where, since the limit of this goes to infinity, I want to do 1 over this, right? So I want to make sure that this is not 0. But if the limit goes to infinity, then of course, in a neighborhood of the singularity cannot be 0. Otherwise, the limit wouldn't go to infinity. So let me pick delta prime smaller than delta, such that for z, such that z minus a smaller than delta prime, and of course bigger than 0, because we can't say anything at a, we have that f of z is not 0. Okay? Yeah, okay. Here I should, the limit to 0 is not a problem, but when I do the limit to infinity, I should really do this with absolute values. Okay. Right, so this must exist. Otherwise, that limit wouldn't be infinity. Okay. But now, this means that if I define, right, so define g of z equals 1 over f of z. Right, then in that set, in that punctured disk, g of z is analytic because I'm dividing by something that's not 0. And of course, the limit, right? The limit of, as z goes to a, of z minus a, right, times g of z, what is this equal to? This is equal to the limit as z goes to a of z minus a over f of z, right? But the norm, the norm of f of z is going to infinity, right? And this is going to 0, so the limit of this must be 0, right? Just take absolute values, right? Okay, this is going to 0, this is going to infinity. Doesn't matter which direction, right? If we can take absolute values. Absolute value of this would be 0. It's 0. So G is a removable singularity. Singularity at A. Okay, but what does this buy us? The fact that G has a removable singularity at A, right? And G is not 0, right? So we know also that G, right, because how it's defined, G is not identically 0. So this means that G of Z is equal to Z minus A to some H, right? There must exist H such that G of Z is equal to Z minus A to the H times Gn of Z, right? Where Gn of A is non-zero, right? Now just take, so now we've written G of Z with something that we know is not 0. What do? We now take and potentially even smaller neighborhood, right? Take theta prime such that double prime, right? We can always take smaller and smaller neighborhoods, right? Take this such that bigger than 0, such that G H of Z is not 0 in the disk, right? Because this is not 0 at A, and it's continuous. This must exist. Okay. Now we can define, in that neighborhood. So in that neighborhood, right? don't forget that we're just trying to understand locally what's happening at a point, right? So it doesn't matter that we're losing, and this global understanding by taking small and small neighborhoods. That doesn't matter, right? We can define fh of z to just be 1 over gh of z as analytic, right? Because gh of z is not 0. Right? And so if we now go and write back what f is, right? What do we have? You write it in another, that's okay. Right? And so, again, in that neighborhood, so in a neighborhood of A, we have that f of z is equal to, right? So now we have to replace, right? We have to replace in that, in this formula here, right? So it would be 1 over g, so 1 over this. So I get z minus a h times fh of z. This should be an h. Okay? Is this clear? If something is not clear, please. Minus h, of course. Right? So if f of z tends to infinity, they must tend at a certain order, just like if it was a 0. Right? And all we had to do was to do the exact same thing on the function 1 over the function. Right? And so we call this, we say that f a is a pole of order h of f. Okay? So if a function is, if you have an analytic function around a point, right? Sometimes if it has an isolated singularity, right? It's singular at a point, but not in the neighborhood. Then, sometimes it's a removable singularity. Sometimes is what's called a pole, right? And maybe other times there'll be other things. We'll get there in a second. But at least for now, if that limit is infinity, it needs to have a pole of a certain order, right? And if it has a pole of a certain order, we can actually write it as, a z minus a to the minus h, which is something we understand, and then something that's non-zero, an analytic, right? And here you're maybe already seeing, like I can already hint at, the fact that if we now try to integrate, right, this function around the closed curve, because it has a characterization of this type, right, then maybe we can understand what the integral is in terms of the Cauchy integral formula, right? And I mean, in a very, very vague sense, this is what residue calculus is about. But we'll get there. In a vague sense. Okay, so a pole is an isolated singularity, right, where we have this. And okay, and of course fh of z is analytic and is not 0, right? Not that fh of a is non-zero, right? Because it was obtained by dividing 1 over g. Okay, so a function. This is an important definition because you'll hear this word many, many times. A function, let's say f. Okay, maybe this is not quite, if I say it this way, I don't want to define it this way yet. So a function, let me just say first in words, a function that is analytic except for poles is called meromorphic. Okay, so if I have a function, right, I'm not saying yet that it goes from a region to C because, at the pole I would have to define it to be plus infinity, so I don't want to do that just yet. But a function that is analytic except for poles is called meromorphic, say, in a region. is analytic in a region except for poles, then it's called a meromorphic function, right? And so this term is very important, right? So in particular, like if G, right, if F and G are analytic, right, say in a region, right, and G is not identically 0, then F over G is meromorphic. Okay. And of course, if I add meromorphic functions, they're still meromorphic. If I subtract, if I take quotients of meromorphic functions, they're still meromorphic. Okay, so voluntary homework. Say homework. Right? This is a good exercise to do, I think. Check, convince yourself, or I say convince yourself that this is the same definition as for polynomials. Right? Remember, for polynomials, if we had a polynomial P and a polynomial Q, we said we talked about what were the zeros and the order of the zeros and the order of the poles. Right? So maybe I'll write this a bit better just to make it. Okay. Okay, convince yourself that the definition of order of poles and zeros is the same as given for polynomials. Right, so in polynomial. Right, in the much earlier in the course, we talked about orders of zeros and orders of zeros and poles of polynomials. Now, what I'm asking is convince yourself that this is the same, right? That this is the same definition, right? Right. In other words, I can write it here. If P, right? If P of Z and Q of Z are polynomials, right? What are zeros and poles and their orders of P over Q of Z? Right. Okay, this is what I'm asking is, right? Convince yourself that this is the same definition that we gave before. It's relatively easy, but it's a good exercise to make sure that this is well understood. Okay, so now let me get into something. Let's try to now characterize, right? Okay, there was a question which was asking why is it that this is meromorphic? An analytic function is also meromorphic. Like, it doesn't have to have poles to be meromorphic. It could just have 0 poles, it's still meromorphic. Like meromorphic is more than being analytic, right? You should think of analytic functions and meromorphic functions. Even a function that has no poles is still meromorphic. maybe I can write here, except maybe for poles. Yeah. Okay, so let F be analytic. Be analytic in a neighborhood of A with an isolated, right? With an isolated singularity. I should say, I mean, just a punctured neighborhood, right? I mean, sometimes I say neighborhood in, right? I mean, punctured. So of A with an isolated singularity at A, right? What I mean by this, I mean that, you know, it's analytic near A, but not in A, but there is a neighborhood around A in which is analytic. Okay. So now we're going to try to understand, okay, and we'll have to do this next week. Right? So for A, we're going to try to understand two behaviors. So one is if for alpha real, right, we have that the limit z goes to A let's say with absolute values, alpha f of z goes to 0. And the second behavior is for alpha real, the limit z goes to A goes to infinity. Okay. So clearly, if this is satisfied for an A, then it is satisfied for every A bigger than that. Right? If this is satisfied for some alpha, then it is satisfied for alpha smaller than this. Right? So picture to have in mind. All right, so let me make sure I get this right. Yeah. So there'll be some, let's call this alpha of property 1, such that maybe, right, such that one, like over here, 1 is satisfied. There's some potentially different 1 over there, but it needs to be on this side, right? So alpha for property 2, such that all the way over here, everywhere 2 is satisfied. Okay, and maybe there's some region which we don't know what happens. Right? This is the picture. This is the picture to have in mind. Okay. Is this picture clear? I'm trying to understand, right? It's clear that something has to do, to understand what happens in an isolated singularity, we need to understand how the limits go to 0 or infinity as we put different powers of z minus a, right? This is one way of checking degree of polynomials or orders of zeros or poles, right? So this seems like something sensible to do. And we can now draw this picture in which we get some alpha. We know that below this needs to shoot off to infinity, right? I mean, think of fz as just a constant, and this would be, right? And this would be 0, right? And then this would also be 0. Okay? And when I go bigger than some constant, it needs to be satisfied, right? So each f has a picture of this type. So what we're going to prove on Tuesday is this sort of classification theorem that says that only two things can happen. Either there is one alpha, and it needs to be an integer, right? It's the order of the 0 or the pole. So either there is one alpha, or first of all, either the function is identically 0, and it's really not interesting. So let's drop that. So that's one option, of course. Then also another option is that there exists one point, let's call this k, which is actually an integer, such that both these numbers are equal to k, right? So we characterize this completely. There is an integer, it's the order of the zero or the pole, depending if it's positive or negative, and everything to the right, this limit goes to 0, everything to the left, this limit goes to infinity. Or if the function is not identically 0, it doesn't have this nice integer that sort of determines everything, then it must be that this is actually not satisfied for any alpha, either of these equations. And when that happens, it's called an essential singularity. And those are very interesting phenomena that I'll describe next week. Okay, and so what we're going to prove at the beginning of next week is sort of that this picture, that there's this trichotomy. There was a question. The question was whether there are, related to the identity theorem, there are related results over the reals. That if a function is analytic, it can satisfy these kinds of properties. The big difference is that the definition of being analytic over the reals was very different, right? The definition of being analytic over the reals is essentially having a Taylor series. And once you have a Taylor series, because it's determined in a neighborhood, you expect that if it then converges elsewhere, then it needs, right? If the Taylor series is the same, it needs to converge to the same thing. But here, our definition of an analytic function had nothing to do with Taylor series. It was just the fact that it was differentiable, right? So this comes more from maybe the fact that the word analytic over the reals means things that actually hold for analytic over the complex plane. But you should keep in mind that for now, all we've defined analytic functions are just functions that are differentiable, right? And so when I make the comparisons to the reals, what I really mean is comparison to differentiable functions over the reals, right? Over the reals, you have functions that are differentiable infinitely many times, but they are not analytic in the sense of the reals analytic, right? And that's sort of the examples that I have in mind. So yeah, maybe I should have made this more clear when I said this. Yeah. Yeah, thank you for the questions. Very helpful. I can stick around a bit longer if there's any more questions.